All right, so at this point, like we've seen the lambda calculus, right? And we hopefully through stuff we did in lecture, through maybe working on the module, even though we haven't seen a formal proof, hopefully you intuitively believe at this point that like you can do any computation you want in the lambda calculus. Even though it's going to be super annoying and tedious, you can do it, right? We saw how to encode data types, like kind of as it unfolds. And then last time we saw how to do arbitrary recursion using this Y combinator thing. So historically, I think I mentioned this before, that like the lambda calculus was developed. It was supposed to be kind of a foundation for doing mathematics. It's like, what if instead of taking sets as being the fundamental things that we build everything else out of, what if we take functions as the fundamental things that we build everything out of, and like can build on top of that and build up all of mathematics. Partly just as an interesting intellectual exercise, partly also to answer the question of, is it possible to, given some mathematical statement, can we kind of decide, have some kind of algorithm or machine that figures out whether it's true or not? And it turns out the answer is no, you can't. But so right, Alonzo Church developed this lambda calculus, and basically it was two of his grad students, I think Rosser and Cleany, I think, who figured out the stuff about the Y combinator, and they're like, hey, you can just do arbitrary recursion in this. And it turns out, we'll see why a little later, that kind of like killed it as a foundation for mathematics, because basically, essentially it means you could use it to prove anything you want, whether it's true or false, doesn't matter. You could just you just throw an infinite loop basically, right? Imagine it's like this. It's like, if you ask me to prove, something to you, I'll be like, sure, I'd be happy to. I'm a little busy right now, but I'll get back to you tomorrow with the proof. And you're like, okay. And so you come back to me tomorrow, and I'm like, yep, I'm going to get that proof for you, but I'm still a little busy, so I'm going to get it to you tomorrow, right? And like, at what point are you not willing to wait anymore, right? So like, this is the problem, basically. You can promise to give a proof of something, and then just like go into an infinite loop, and it's like, is that a valid proof? It shouldn't be, but so what Church then did was to add a type system to the lambda calculus to rule out programs that would loop forever. Okay, so that's what we're going to study next. And so I want to talk a little bit first about like what are type systems, like why do we use them? And for those of you who had programming languages with me, you've probably heard me talk about this before in a similar way. So what are type systems for? And there's a number of ways you can answer this question, right? And they serve multiple purposes. But this is one way to look at it that corresponds to why a type system was added to the lambda calculus. So we've got here, this is some space of like all programs. Let's say we just take some particular language, right? And some of the programs are good programs, and some of them are bad programs. What do we mean by good and bad? Well, it depends. There's different things we could mean depending on what we care about, right? So maybe bad programs for us are, programs that crash. So we want to say, I don't want to write a program that's going to crash when I run it, right? I want to make sure that my programs don't crash. Or, maybe you don't want them to get stuck, or you don't want them to, as in the case of the lambda calculus, you don't want infinite loops, or infinite recursion, right? Or maybe you care about like security, like they like leak secrets. Etc. Okay, you can make a very, very long list of properties that people care about that programs have, right? And the point is, well, we have some kind of programs, we want them to have certain properties. How can we make sure that the programs we write have, these good properties and don't have these bad properties. And so one way we can do that is with a type system. So a type system a type system is a way of saying, I'm going to consider certain programs okay, like programs that I can give a valid type to. I'm going to say those are okay, and I want to make sure that any program that has a valid type is a good program. Okay, so it's an if, right? It's a if it has a type, then it's a good program. Okay, but it's not an if and only if, and this is actually a very fundamental limitation. So there's some good programs out here. So here's some good programs. Right, so the programs out here are they're actually good programs, they work fine, they don't have whatever bad features we want, but they don't have a valid type. So that's possible, right? It's possible that there's some things that our type system doesn't capture, stuff that would actually be good, but our type system can't kind of show it. And it turns out, right, and so maybe you can also imagine some kind of other analysis that shows for sure that a program is bad. And so you can find tools like this where you can run certain kind of analysis tools on your program, and it's oh, there's definitely a bug here, it'll definitely crash or do this, right? But in the middle is this dark, chaotic abyss. So this is the abyss. If I knew how to draw, I'd draw little dragons and stuff, little sea monsters. Okay, and this is actually there's something called Rice's theorem. You can go look it up later if you want. And of course, there's a very formal mathematical way to state what this theorem says, blah, 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 but essentially what it says is any interesting property of programs is undecidable. That is, any property you could care about. The most famous one is the halting problem. Does a program stop or could it loop forever? Right? Or you could say, does a program crash? Does a program leak secrets? Does a program, right? Any of these things you might care about, any interesting property of programs, it is not possible to say yes or no, does this program have this property or not. You could maybe say it for some programs or for others, but there's always going to be programs where you cannot, there's no program you could write that would take other programs as input and tell you yes or no, right? So no matter what we do, a type system is always going to carve out some subset of good programs, but it's always going to miss some. It has to, because Rice's theorem says you can't possibly exactly cut along that line and figure out exactly what's on this side, what's on that side. So that's just the way it is. So we kind of, it's a trade-off, right? In order to get the safety of knowing for sure that anything that passes the type system is good, we give up some other programs we can write. And we say, well, I'm not allowing myself to write those because I'd rather have the safety than being able to write any program I like. Or it might mean that some programs we have to kind of rewrite them somehow to move them from here to a similar program over here that does the same thing, but the type system actually accepts. Right? And a lot of research in type systems is can we push this boundary out, do something a little more complicated and push that boundary out a little more and accept some programs that we didn't accept before, right? That's what was happening with the Lambda calculus, that they said, some Lambda calculus programs can have infinite loops, we don't want that. And so can we come up with a type system that rules that out? And of course, this led directly, not directly, but eventually Haskell itself is descended from this line of work. That kind of got thinking about adding types to the Lambda calculus. So, but it relates to lots of other cool things as well. So, type system, or this is simply typed Lambda calculus, or STLC. Every single time I say either STLC or SLTC, I'm really confused permanently because they're both meaningful acronyms that are very similar. So let's think about how this works. So here's, whoops, why did I do that? All right. So our goal is a type system for Lambda calculus that rules out non-termination. Non-termination, aka infinite loops, or infinite recursion. Okay, so things that have a valid type should definitely stop. Things that don't have a valid type, well, they might stop or they might not. Right? We don't know for sure, but this is the goal. So I want to be able to say things. So remember, just as a reminder, we have the lambda calculus, right? It has variables. It has lambdas, and it has application, right? And I want to come up with, let's see, we're going to use, for our types, I'm going to use we'll use alpha and beta. We use Greek letters to distinguish types from other things, but maybe alpha and beta, it's kind of like A and B, which we're used to in Haskell seeing types written with A's and B's, right? So the first question is, what kind of types do we want? And think about what kind of types Haskell has, and what kind of types we need for these things. Well, a lambda is supposed to be a function, right? So we definitely want some function types, right? So for one thing, we'll definitely have types like function type. And besides that, there's not really anything else that we have, except we need some kind of types to be like a base case. Because if all we had is that, well, a type is a function from one type to another type. Well, what are these types? Well, they have to be functions. Literally the only thing we have is a function type. The only thing you can make is infinite function arrows all the way down. So we're just going to add some I'm just going to say or I'll just say capital A, B, C, dot. These are base types. Right? Imagine we could have bool and int and char and stuff like that. It doesn't really matter what they are. We have some kind of collection of base types. And we could, if we had int, then we could, if we wanted, we could add to this language things like plus and times and other things. But for now, we're just studying the basic, lambda calculus. Adding extra stuff like that is pretty easy, and it doesn't really change much about what we're going to talk about. So these are all the types we need, actually, because all we have is functions. So we've got some base types, and we've got functions. And so what I want to do is, we're going to make some rules that say, what type does each kind of term have. So if I have a lambda, what type is it? If I've got an application, what type is it? How do I decide what type it is? And we're definitely, I want to see if we can if you all can figure this out, if we can figure it out together, and definitely use everything that you've learned about Haskell to help, right? This is going to end up being very, very similar to what Haskell already does, right? How these types are in Haskell. So I want to be able to say things like, I want things of this form, some term has type, maybe I'll put two, I don't know. In Haskell uses 2 colons for has type. Everyone else in the world reason that there's this difference is that when Haskell was being designed, they were like, you know, lists are super common. Like, people are going to be writing list stuff all the time. So wouldn't it be neat if the cons thing for a list is just a single colon, and it will make, you know, type a double colon, because people won't be actually writing types as much because Haskell can infer all the types. You don't actually need to write them. Anyway, that was a very short-sighted decision.
Yeah, didn't that end up being the opposite?
Well, yeah, it kind of ended up being the opposite. Like, number one, yeah, we write list stuff some, but like often we work in terms of higher abstraction. Like, we just write map and fold and whatever. We don't actually like pattern match on cons. And we write types all the time because, yeah, it can infer them, but number one, it's helpful to write the types because it helps with documentation and it helps with better error messages. And actually, Haskell has added a number of, like, original basic Haskell, it could infer all the types, and that was a big selling point. Like, you never have to put a type signature if you don't want to. With various extensions that you can turn on now, there are some things where, like, no, if you use this extension, sometimes you have to give it a type signature for it to be able to figure it out. Anyway, so it's kind of backwards now, and but we're just stuck with it. Like, if Haskell were to change that now and switch those, it would break, like, every Haskell program ever would not parse, and so it's just like, that's not going to happen. But any other language that you see, like, we're going to learn a language called Agda in a little bit, and it does the opposite, right? A single colon means has type, and a double colon is for list con. Whatever, figure it out. All right, that was a tangent. So this is our goal, is to come up with some rules that tell us, you know, when does a certain term have a certain type. So let's first think about I'm leaving some room over here on purpose because we're actually going to need to like put something here, but we'll get to that. So what do you think? If I have something applied to something else, right, which is supposed to be like function application. Like, first of all, what do I need to know about the types of these T1 and T2 things? And then how do I use that to figure out what type the whole thing has? And again, you know, think about if you were, you know, if you had fx in Haskell, what type does it have, and how do you know? Any ideas? Alexandra?
Like, is T1 or T2 a function type or a base type?
Which you're asking?
I mean, it seems like T1 would be a function type
Yes.
because it's applied to T2.
I totally agree, right? T1 had better have a function type because we're using it like it's a function. We're applying it to an argument. Okay? So totally agree. So we need, I'm going to make this bigger. We need T1. And does it have to have a specific function type, or could it be anything?
Anything?
It could be anything, right? I mean, so we'll just say, you know, alpha, arrow, beta. Okay? What else do I need to know? T2 had better have type alpha. Totally agree, right? Otherwise, it doesn't make sense. Right? In the pure Lambda calculus without types, we can apply any term to any other term, and it's totally fine, right? But if we're keeping track of the types of things, then yeah, if T1 says it takes type alpha as input, then we better give it that type. Otherwise, it doesn't make sense. So I need to say T2 has type alpha, okay? And then what goes here? What's the type of T1 applied to T2? Beta, right? Yeah, it's the alpha type of the voltage. All right. Cool. What? If I just see a variable x, what type does it have? It's a trick question. What was that? And how do you know?
How? I mean,
Yeah, so it's a trick question. The answer is like, I don't know. Like, what? It's a variable. How do I know? How am I supposed to know what type it has, right? So the point is that we're actually going to need to add something very similarly to when we were doing rules for propositional logic, where we actually need something extra, which is we need a context that says, you know, what are the variables that we know about right now and what types do they have? Because when I see a variable like in a lambda, we'll see that in a second, I'm like, oh, okay, this variable is an int. So I'm going to remember that x has type int, or whatever it is. And the next time I see x, I'm like, oh yeah, I remember x. That's supposed to have type int, so, okay. So we're going to need to add, okay, so this, again, we read this similarly where we say, you know, given some assumptions in this context gamma, and in this case the assumptions are telling us the types of different variables. Okay, so gamma is basically as a context of variable types. Right? Think of it as like it's a map from variables to types. Right? And if you were going to implement this in Haskell, you could literally implement it as a map. It says, well, if you give me a variable, I can look it up and tell you what type is associated with that variable. Right? Or it could be like a, you know, in Python it could be a dictionary or whatever. Okay, and in this rule I'm just going to add it everywhere, right? We just need to like pass it along, right? We're like, well, this is what I was assuming about all these variables, so I'm just going to pass that along to both of these things, but nothing is changing about it, we're just going to pass it along. Okay, but here, right, I want to say, right, that, well, I need to look up, say, look, if I have x in this context, if I've assumed the type of x is alpha, then I can just say that type of x is alpha. Right? In particular, this rule doesn't, like, if I don't know, if I see a variable and it's not in my context, then I can't give it a type, because I don't, like, I'm like, what is that? What is x? You told me about x yet. I have no idea what type that is. Wrong, and no, you know, it doesn't have a type. Okay, and this would be like, if you're type checking something, remember, like, think about when you're writing a Haskell program and you misspell a variable. Or you use a function and you actually haven't implemented the function yet. Right? Haskell yells at you and it's like, I don't know what that variable is. I can't type check this because I haven't seen that variable, right? That's exactly what would happen here. But if we do have that variable in our context and we remembered that it has type alpha, then we can just say that's type alpha. Okay, and then the last rule, which is in some sense kind of the most interesting rule, I don't know. Okay. If I see a lambda, what type does it have? How do I know? What is that? It's a function. It's a function, for sure. So, you can at least write this. It better be a function. That's what lambdas represent. They represent functions. Okay? Any thoughts on what should be the input and output types of the function?
Well, the input type would be T, right?
The input type would be T.
Like the type of T.
The type of T.
Or is the dot, are you using the dot as like a function composition? Or are you using
No, it's just part of the syntax of
period for
Lambda.
that?
Yeah, maybe I
Okay.
should write it. I don't know, here. Let's actually, I always forget, like this is, anyway. We should write it like this. Like in Haskell it's written that way. Right? In math usually it's written with a dot, but there's no particular reason that I need to if you memorize more syntaxes. So, I mean, I think we've seen it with the dot before. The arrow is potentially confusing because it looks like a function type. Right? I don't know. Well, you know what, I'm pretty sure we've used the dot before when we talked about, like when you used the Lambda calculus evaluator for your problem set, you used the dot, yeah. So yeah, the dot is just separating the function argument from the body. Okay. So yeah, what input and output types does this have? So you said something about the type of t. So how does the type of t relate?
Or you're giving that as the input to the function.
T is not the input to the function. Right, t is like, this says, I'm a function, I'm going to take something named x as an argument, and then I'm going to return t. So t is like the output. Okay.
Oh, so X,
What was that?
so whatever X is, that two.
Okay, yeah, so like the type of x goes here, and the type of t goes over here. Yeah, I agree. Now, here's the weird thing. How do we know what the type of x is? We can ask what the type of t is, and so if we have some kind of rule that says, you know, okay, so this is actually an interesting problem, and if, like, Haskell lets you do this. Haskell lets you just write lambda x arrow t, and it somehow figures out the type. But it turns out that it actually has to use some kind of interesting and non-trivial algorithms to do that. Because it basically says, well, I don't know what the type of x is yet. I'm just going to kind of remember that I don't know what it is, and as I keep going, I might learn more things about what type it has to have. Like, depending on how x gets used inside of t, it's like, oh, you did x plus 3, so that means x must be an int. So now I can go back and like fill in what I know about x. We're not going to do that. So we're actually going to add, for the purposes of talking about the type Lambda calculus, we're going to add something here. Maybe I'll do this in like parameters. We're just going to say, okay, no. When you write a lambda, you can't just say lambda x dot t. You have to actually say what the type of x is, because otherwise we can't guess what you had in mind. Like, you can, it is possible, but it's more complicated. So we're just going to say, to keep things simple, if you make our lambda, you just have to say what type the input is so that we know right away. Okay, so that makes it a lot easier, because now okay, well, so now, of course, this is a function from alpha. And then what do I have to put above the line? So above the line, I have to figure out what the type of t is. So like, if the type of t is something, if t has type beta, then it's alpha to beta, right? So it takes x as input, which we said has type alpha, and it gives t as output, which, you know, this thing up here says, well, if t has type beta, then lambda x t alpha beta. There's something missing, though. It's a little subtle. I wonder if anyone has an idea of what is missing, or what could go wrong. Alexandria?
Do we need X at the top?
Yes, we need to mention x at the top. Why?
Because we're just kind of concluding at the bottom that X is type A and not really proving it. We're just saying that it is.
Yeah, well, we don't need to prove it because we're kind of told that. Like, the fact that we see this lambda x colon alpha means we're just being told x is type alpha. But I definitely need to talk about x up at the top. Anyone have any idea? Why is it important to say something about x? that thing on the top. Sammy? So it'll be in gamma, yeah, and why do we need it there?
So that we're doing application.
So, I'm not sure I quite understood you. So you're saying something about we're using an application rule?
So if we use, or if we apply this Lambda expression to prove that we, or prove the type of that application, that's type alpha.
I don't, so if we're applying this to something else, like I just need to know that that something else also has type alpha. I don't really need to know anything about X to talk about that other thing, right?
Is it almost like it implies you would have to know the first part of it to know the second half? Or no?
Yes. Yes, but I think there's maybe a simpler way to understand why this is important. So, okay, remember T could be anything, right? It could be any complex term. And if I'm writing a lambda x t, x could show up inside t. It probably does, right? It's possible to make a lambda that ignores its argument, but that's kind of boring, right? Most interesting lambdas are gonna, introduce this argument x and then use x inside t. So when I'm asking what the type of t is, eventually I'm gonna get to x somewhere. And like the way this is written right now, at that point I would be stuck because I'm like, X, what is X? I haven't heard of X, right? Because we didn't add X to our assumptions about variables and their types, right? This is where a variable like goes into here. It's like, oh, I see a lambda, so now inside of that lambda, now I know about a variable named X, and I have to remember what type it is. Okay, so that's why I have to say. Okay, well, we're gonna see what the type of t is, but while we're figuring out the type of t, we're gonna remember an extra fact. We're gonna remember that x, if you see an x anywhere, that has type alpha. Right? Or put another way, like we get an extra assumption. We're like, okay, from inside here, I get to assume that x has type alpha, and now I'm gonna proceed and see if I can figure out what type t is.
Yeah.
Right?
Because I see why I was saying what I was saying also.
Okay.
Because moving from left to right, you have to have the.
Yeah. No, yeah,
you can't
you're
assume,
right.
because you
That's
can't
right.
assume that
Exactly.
without it.
Yep. Any other questions so far? Okay, so this is it. This is the final complete version of the rules for the simply typed lambda calculus. And obviously, well, let's see, there's many directions we could go, but so remember, the original goal of this was to rule out lambda calculus terms that never stopped computing, that just like got into an infinite loop. The proof of that, to prove that this does not allow terms which go into an infinite loop, is interesting and non-trivial, and I'm not going to show you that proof. It would probably take like a couple of days of class. If you're interested, I could point you to a good place you could read about it, but you could just take my word for it. The basic idea is, like, the things that looped tended to look like this. So stuff like lambda x dot xx, right? Or like the y combinator that we drew had something like that, like, at lambda x, f x, or, it ended up having things applied to themselves. And if you think about how you would come up with a type for this, like, you can't. Because, like, what type would x have to have if you can apply it to itself? Right? Well, x has to be a function, alpha to beta. But what would alpha be? Like, x would itself have to have type alpha because you're applying it to itself. Right? Well, if basically that means that the type alpha equals alpha arrow beta. That doesn't make any sense, right? Unless you can have an infinite type. Arrow beta, arrow beta, arrow beta, arrow beta, arrow beta, like, and then we don't allow infinite types. So that's not allowed. So I guess it's easy to see why this no longer allows this. What's harder to see is like, well, maybe there's some other super clever way that we could get away with doing infinite recursion that doesn't use this. But no, it turns out that there's not. Right? Something else I was going to say. All right, but let's see. Let's do this. What I want to do is this tool here. Let's see. Okay, so I just made a copy of these, and I'm going to do something, and tell me what you see. Okay. You get to squint a little bit because things are now spaced out here, but
Aren't those the rules we went over?
exactly, right? This should look very familiar. Like, what are these? So this is,
The elimination for implies.
yeah, which one? So like this,
Top.
this is the implies the rule, right? This is the implies intro rule. This is the axiom rule. So what's going on, right? So there's actually a deep connection between these two things. And this is why I did all that stuff about doing those proof rules, which maybe at the time seemed a little weird, like what does that have to do with functional programming? But so I'm going to add the terms back in, but talk about what's going on as we do that. So which color should I pick? Orange. So the way to think about this is, right, these are the rules that we saw before for propositional logic. Well, but only for implies, right? And we'll talk later about, we had and or and stuff like that. And so we'll talk about them a little later, probably next time. The lambda calculus terms can be thought of as proofs of these propositions. In other words, like the lambda calculus term that I put in each place kind of encodes the structure of the proof itself. So like whatever tree you would have made to do the proof, like the lambda calculus term that you write here, kind of itself encodes what that tree would look like, or what the evidence is for that. Or another way is, if I say a certain proposition, and if I claim that a certain proposition is true, I'm implicitly kind of saying that there's some computation I'm willing to do. So for example, if I say, A implies B, I claim A implies B is true. One way you can think of that is, if you give me an A, then I will do some computation to it and give you back a B. Right? I promise that I will always do that. And the lambda calculus term that would go here encodes what that computation is that you were promising to do to kind of show that that proposition is true. So, T or I'll say encodes a proof of the proposition alpha. Well, and I'm saying proposition alpha, right? But even that, I'm punning a little bit, because when our alpha is a type. We started out by saying those are types, but now we're saying, well, look, actually that looks very similar to propositions. Like I've got some kind of base things that represent primitive propositions, and then I can think of this as a function arrow, or I can think of it as implies. Alexandria?
I guess it's kind of going back a little bit, but can alpha and beta be the same type?
Sure. You mean like in this rule here? Like here?
I guess, yeah.
Yeah, they could be anything you want, so they could be the same. They could be different.
So then, so could it be like, earlier we couldn't have like X implies X? If alpha and beta are the same thing, can't you just say alpha implies alpha sometimes, or
Well,
something like that?
you mean like I couldn't have like lambda x dot x x or something?
I mean, it makes sense like why you can't do that.
Yeah.
But at the same time, if alpha and beta are the same type.
Yeah, well, alpha and beta being the same is fine. Like alpha implies alpha is okay, but it's still not true that like that whole thing is equal to alpha, right? Like, yeah. Because then alpha would kind of contain itself as a sub-piece, and it would have to be in there. Is that answer your question? Okay. So I'll fill these back in. Quick, and we'll pick this up next time, and we'll talk more about this. So, going back to here, this is just saying, look, instead of just assuming that alpha is true, some proposition, I'm actually saying, well, look, X, like, stands for a proof of that proposition. So if you have not only the knowledge that it is true, but you actually have a proof of it, then, yeah, I can just hand you back that proof and say, here's your proof that alpha is true. Right? This one says, right, if I have a proof that alpha implies beta, that is a function that says, hey, if you give me a proof of alpha, then I'll do some computation to it and give you back a proof of beta. That's what it means for alpha to imply beta. Whenever alpha is true, whenever you have a proof of alpha, you can turn it into a proof of beta. So if I have that kind of like this little machine that turns alpha proofs into beta proofs, and then T2 is actually a proof of alpha, well, I can hand T2 to T1, and T1 does its thing and turns it into a proof of beta. Right, so that's what we're saying here. this one says, oops. Look, if you suppose that you have a proof of alpha named x, and given that assumption, you can come up with a way to prove beta, and we'll call that proof T, right? Then we'll say that's like proving, that's how you prove an implication, right? You prove an implication by supposing, alpha, and then under that supposition you can prove beta. So it will encode that entire proof that kind of whole process of assuming that you have a type alpha, or a proof of alpha, and then getting a proof of beta. We'll write that as this lambda expression. And that is going to represent our proof that alpha implies beta. It's a little mind-bending because we're suddenly playing with so many concepts at once. There's like Lambda calculus, which is representing, we could think of as just a programming language. And then we're thinking about it as types, but then we're also thinking about proofs, like propositions, and proofs of those propositions, and it is mind-bending because it is actually this very deep connection between these things that really, in some sense, they're the same thing, right? Thinking about programs that have certain types is really the same thing on a deep mathematical level as thinking about proofs of certain propositions. And this is the basis for how I think I mentioned that there's computer systems like programming languages that let you actually write down formal proofs of things that the computer can check. And that's kind of where we're going next, is we're going to actually see one of those systems. But this is kind of the basis for it. So next time, we're going to write, when we talked about propositional logic, that we have more stuff than just implies. We get and, or, top, bottom. And so the next time we're going to talk about, well, what do those correspond to in the Lambda calculus? Can we add stuff to the Lambda calculus that kind of helps us encode proofs about and or and stuff? And yes. And spoiler alert, they will correspond to familiar things that you've seen before, like in Haskell. All right. So I decided we're not going to have another module this week, just because we didn't have Monday, and we were just not quite as far along as I thought we might be. But I'm guessing none of you are going to complain about that. So I will have module whatever we're on now, whatever number we're on, will be assigned. There'll be one assigned next Wednesday. We'll be with all Wednesday, but there won't be Wednesday. All right. See y'all on Monday.